In previous lecture, we were looking at solutions and mentioned at that point that we would go on and take a look in Chapter 5 at some solutions that dealt with a specific group of chemicals called acid and bases. Now, chemists, as did other groups of scientists, of course, were interested in categorizing, grouping, then chemicals that were similar so that we could use it to predict behavior of some unfound compounds at that point or to understand then the relationship between one group of compounds and another. Biologists, of course, had done this for many years in terms of categorizing plants, animals, species. Even sociologists and psychologists classify people into certain categories. So chemists were no different, and so they were looking for ways to categorize. One of the things, of course, the result of that is the categorization of the elements that make up our periodic table is on that same basis, trying to put things together that are similar. Well, in some of their work, some of the early chemists noticed that there were chemicals that when they were dissolved in water had some characteristics that were similar. They had a sour taste. They would turn litmus. Litmus is a natural dye, pigment from the litmus plant, and the litmus from the plant then will be red when it's placed in this kind of solution. They also noticed that the solution had just a water-like feeling from the standpoint of touch, and also they noticed that it would conduct a current. In other words, that it was an electrolyte. We talked about this in Chapter 4 dealing with solutions. We talked about that when materials dissolve, they can either dissolve as ions and we get a conducting solution that we call an electrolyte, or a non-conducting, which means that it went in as molecular. So that was one group of chemicals. Another group of chemicals that were being noticed that when we put them into solution had a bitter taste. And turned litmus blue colored instead of red colored. Had a slippery feeling to the solution. For instance, when you would get it on fingers and rub, it would feel real smooth like soap. And also had the ability to conduct a current. So in other words, it was also something then that was ionic when we put it into solution. Well, the first of these groups was given a name based on the idea of sour, or the Greek for it, which is acrid or acid. And so this group of chemicals then became known as acids. And the other group, because of the place that they came from, were referred to as bases. They were from the earthen materials, and therefore basic in structure and referred to as bases. Now, the question was then, what is it that really gives a chemical this set of properties or this set of properties? And of course, that's what some of the early chemists then were beginning to look at. And one of the first to categorize chemicals then as acids and bases depended upon their chemical structure was a chemist by the name of Arrhenius. Now, Arrhenius also had a lot to do with our understanding of the electrical conductivity of solutions, because he would find that if we took a material as a solid, it might not conduct a current. Now, metals do. That's one of their properties. But sodium chloride, for instance, table salt, as a solid, if you put electrodes to it, doesn't conduct a current. But if we put sodium chloride into water, the solution conducts a current. And so Arrhenius was curious, why is that so? What is happening to the sodium chloride then when it dissolves that it allows to conduct a current? And of course he explained then the idea that when we dissolve certain materials, the water, the solvent molecules, pull the particles apart into charged particles that we call ions. We know that a salt solution is a sodium ion and a chloride ion. And so Arrhenius had a lot to do then with our understanding, first of all, of the electrical conductivity of solutions. Now, looking at those chemicals that had sour taste, changed litmus red, conducted a current, what he found that they all had in common was that they all had an ionizable hydrogen. Now, it didn't mean that they just had hydrogen in the chemical formula, but that when the compound was put into water, one of those hydrogens, at least, or more, had to go into solution as charged particles, as hydrogen ions. And so that's what we mean by an ionizable hydrogen ion. Well, then as he looked at what the chemical composition was for the bases, he found that they had an ionizable hydroxide ion, a negative charged pair. This is not just a single, it's an oxygen and a hydrogen hooked together, which has a negative charge. And so therefore, that was the first chemical definition of acids and bases. Arrhenius's definition that an acid was any chemical that contained an ionizable hydrogen when put into water. A base was any chemical compound that had an ionizable hydroxide when put into water. So that was then the first definition for acid and bases. Now, as chemists began looking at many, many different compounds, they found that there were some materials that had the properties of bases. In other words, they were bitter, turned litmus blue, would react. By the way, one of the other characteristics is that acids and bases will react with each other and neutralize each other's properties. In other words, if I put a base in with an acid, the sour taste disappears from the acid and this bitter taste disappears from the base. They neutralize each other or cancel each other out. And so they found that there were other chemicals that had properties similar to these that Arrhenius had already categorized as bases, that had no hydroxide in them whatsoever, and yet they had the same chemical behavior. So the definition needed to be expanded. Two chemists, two different countries, but at about the same time proposed a new definition for acids and bases. The two chemists were Bronsted and Lowry, and we call the definition then the Bronsted-Lowry definition, but this is not one name. This is two individuals who proposed basically the same definition at very nearly the same time. They both were looking at this right up here. They said, what in fact is a hydrogen ion? What's a hydrogen ion? And what they then looked at was the atomic structure of the hydrogen ion. And in the next chapter, in chapter 6, we will be talking about atomic structure. We'll be talking about the subatomic particles, electrons and protons and neutrons. But in their study then, they realized that a hydrogen atom then, which is neutral, an atom itself, as all atoms are electrically neutral, a hydrogen atom consisted of one positive charged center called the nucleus with a +1 charge, and surrounding it a negative charged particle that was defined as an electron. And so a neutral hydrogen atom, and we show electric neutrality here by showing this little superscript 0. That just means a neutral atom. A neutral atom of hydrogen then had this positive charge and an electron. Now, a hydrogen ion, which must have a positive charge, then means that it must have lost that electron to something. We're not even worried about that. But the fact is that a hydrogen ion then is merely the positive charged part, which is called the proton. This is the proton, and this is the electron. And so, therefore, a hydrogen ion was merely a proton. That's all a hydrogen ion is. One single proton. Now, what Bronsted and Lowry said then, when we put something with an ionizable hydrogen into the water, if it's acting as an acid, that proton must be given to something, must be given to the water molecule, must be given to something in there. And so they decided to define an acid then as anything that was a proton donor. Anything that would give up a hydrogen ion to then the solvent was called then an acid, a proton donor. Well, if one defines an acid as a proton donor, then of course the logical thing, because of the opposite properties of bases, would be to categorize a base as a proton acceptor. Anything that could accept a proton was then a base. Now, did this mean that the hydroxide that Arrhenius had proposed is no longer a base? No, because that OH minus, a negative charged species, certainly should be able to attract a proton, an H plus species. As a matter of fact, if we do that, we would see then that we would have H plus being attracted to the OH minus, and what we would get would be H2O. We would get a neutral compound. So we see how the hydroxide then neutralizes the acid property of the solution, or vice versa, how the acid neutralizes the base property of a hydroxide solution. So the hydroxide ion could accept a proton to make water, and therefore it was serving as a base. So it didn't change anything as far as the base here, but what it did was it added a whole new group of chemicals that could be bases and not have hydroxide ions in them at all. And so all of a sudden we had many, many materials that fell into the category of bases. For instance, ammonia, NH3, is a base. And if we put it into a solution, which let's say has some hydrochloric acid, we will get a product of NH4 plus and Cl minus. If we look carefully at it then, the ammonia has accepted, notice to go from here to here now, it had to do what? It had to gain an H plus. So it accepted a proton. Where did it get the proton from? It got the proton from the HCl. The HCl was the one that was donating the proton then. So the ammonia was therefore acting as a base, and the hydrochloric acid, the HCl, when put into water, was acting as the acid. Well, we notice that ammonia doesn't have any OH in it at all. And so, therefore, we had to have a broader definition to identify bases, because this was going to act just like a hydroxide ion in it. As a matter of fact, if we put ammonia into water, we get a chemical reaction in which we produce ammonium, positive 1 ion. So once again, to go from here to here, it had to gain a hydrogen ion. Where did it gain the hydrogen ion? Well, it gained it from the water, And when we gave up a hydrogen ion from the water, we end up with a hydroxide ion. So we generate a hydroxide ion from the base reaction, but we didn't start with hydroxide ion in the initial compound itself. Well, other things, again, that have no hydroxide in them whatsoever. For instance, hydrogen carbonate ion and sodium hydrogen carbonate. The chemical sodium hydrogen carbonate, for those of you, of course, that are in the laboratory part of it, you did an experiment using sodium hydrogen carbonate called baking soda. Baking soda, then, the hydrogen carbonate part of it, will react with water and produce H2CO3, called carbonic acid, and hydroxide ion. Again, if we look at this, how did it get from start to finish? It gained a proton. So the hydrogen carbonate ion now is acting as a base because it is accepting a proton. It accepted the proton from the water, and the water ended up as OH. So obviously, if this is acting as the base, the water is acting as the acid. If ammonia is acting as a base, water is acting as an acid. Up here, ammonia is acting as a base, and the HCl is acting as an acid. But in each case, then, we have something that is accepting a proton and something that's donating a proton. Now, anytime we talk about acid reactions, we automatically must include base reactions. Anytime something's going to donate a proton, something has to be there to accept it. So acid-base reactions always have to go hand in hand then in our discussion. So once again then, the definition that Bronsted and Lowry both came up with was that an acid is a proton donor and a base is a proton acceptor. Now, when we looked at the conductivity of solutions, we looked at some examples, or looked at least one example of what we call a strong acid, and we looked at one example of what we called a weak acid, and we looked at one example of a strong base and a weak base. The characteristic of the strong acid and the strong base was that when we put those into water, we had strong electrolytes. A lot of ionization had occurred. When we put the weak acid, vinegar, and the weak base, ammonia, in water, we found that we had just a little bit of conductivity. In other words, most of the material dissolving went in as molecules, not as ions. All right? So let's take a look at how we can break down and take a little look at the chemistry then of what we categorize strong acids and weak acids. All right, first of all, looking at strong acids, and we could write the chemical reaction here. If we put a strong acid, which we'll just call HA, in water, the acid donates a proton to the water, giving us then the hydronium ion. This is an ion that we haven't mentioned before, but this H3O plus species here is called the hydronium ion, H3O plus. And the negative ion of the acid, whatever it is. So A could be Cl, A might be Br, whatever the case is. A here is just representing the negative part of the acid. All right? Now, one of the characteristics of strong acids is that they are nearly 100% dissociated. What that means is then is that the molarity, the concentration of the hydronium ion in a strong acid is equal to the initial molarity of the acid itself. In other words, if it's 100% dissociated, if we make up a 1 molar solution, of a strong acid, we're going to end up with 1 molar hydronium ion. 100% of the molecules fall apart, all right? So that's a strong acid, something that ionizes nearly 100%. Now the little brackets around the hydronium ion that we see here, and we'll see this now the rest of the text actually, those little brackets there mean moles per liter. So anytime you see an ion or a compound in brackets, it means that we're expressing its concentration in units of moles per liter. So what we're saying here is that the molarity of the hydronium ion is in fact equal to whatever the molarity of our initial acid was. Now, what acids do we have that are strong acids? Well, these are the common strong acids that we find. Notice that the first 3 all come from one family. And we talked about that family when we talked about the organic chemistry. We talked about the halogenated hydrocarbons, the halogen family, which the halogen family is this column over here, fluorine, chlorine, bromine, and iodine. 3 of those, chlorine, bromine, and iodine, all form strong acids. Hydrobromic, hydrochloric, and hydroiodic acids. Again, we haven't done the naming yet, so we're not concerned about exactly how we name things. We'll do that in Chapter 8. But called hydrobromic, hydrochloric, and hydroiodic, those 3 acids are strong acids, meaning that when we put them in water, they're 100% dissociated. One might say, well, what about hydrofluoric acid, seeing that it's kind of in that same group? Well, it turns out that hydrofluoric acid is in fact not a strong acid. It doesn't highly ionize when we put it into water. And we'll talk a little bit about that when we talk about chemical bonding in a later chapter. The other ones here are the common acids, nitric acid, sulfuric acid, and then this one right here, which is called perchloric acid. Perchloric acid, and those are then the most common of the strong acids. Those are the ones, once again, that when we put them into water will be nearly 100% ionized. Now, what about weak acids? How do we demonstrate or explain their relationship to a solution then? Well, in the weak acids, we can again write the same general equation. You notice it doesn't look any different than what it did for the strong acid. Here's our weak acid with water. The acid donates a proton to the water, and we get a hydronium ion and an anion. Remember, cation is a positive ion, and anion is a negative ion. But the difference is this, and that is how much hydronium ion we have in the system. The amount of hydronium ion we have, in this case, is not equal to the initial molarity, because only a small amount is actually undergoing reaction. As a matter of fact, the hydronium ion concentration in a weak acid is equal to the initial molarity times the percent ionization divided by 100, in other words, a decimal instead of a percent. So if something was, let's say we had a weak acid which had a concentration of 1 molar, and we found out that it was 5% ionized. In other words, 95% of the acid stays as molecules, only 5% actually undergoes this reaction to form the ions. So therefore, the hydronium ion concentration would be 1 molar times 5 over 100, or 0.05 molar concentration of hydronium ion. 95% of the acid would still be molecular in its form. So weak acids then are chemicals which undergo then only partial ionization when put into water solutions. Well, what are some of the weak acids. Well, let's take a look then at a table showing us some weak acids, and many of these are somewhat common chemicals, things that you probably have encountered before. We'll look at, first of all, a few of these I'll pick out, and then we'll come back and talk a little bit more about a couple of others. But let's start right here. Acetic acid. Acetic acid, we've heard that term. Acetic acid is the acid that's in a water solution making up vinegar. So that's the acid that is present, acetic acid. Boric acid. Here's the chemical formula for boric acid, H3BO3. It's a weak acid. Boric acid, a couple of commercial uses. Boric acid, weak solutions, or dilute solutions, I should say, of boric acid have been used many years as an eye wash for a pink eye or some slight mild eye infection. Boric acid has been used as an eye wash. Also, boric acid is one of the major components in roach killers. If you look at a little can of roach killer, you'll probably see as one of the major ingredients there, boric acid. So it's toxic, at least to certain types of insects. The advantage is that the insect eats it, it then goes on back to its hiding place, and the chemical kills it. It also sort of acts as a little bit of a preservative, so it doesn't give off any odor as it decays. Let's go down here to, well, we can talk about carbonic acid just a second. Carbonic acid, H2CO3. This is the acid which is used, actually we add carbonic acid to carbonated beverages. And the reason that it is added is because carbonic acid not only ionizes as an acid, in other words, acts as a proton donor, but one of the other characteristics of carbonic acid is that it is unstable temperature-wise and decomposes into water and CO2 gas. This is what it is that gives us the fizz in a carbonated beverage, is the carbonic acid. When you take off the cap, the carbonic acid starts to fall apart, and as it falls apart, it gives off little bubbles of carbon dioxide. That's where the fizz comes from. So most carbonated beverages have an appreciable amount of carbonic acid in them. All right? Nitrous acid, let's take a second to talk about it. Nitrous acid, now remember we had HNO3, which was nitric acid, HNO3, nitric acid, which is a strong acid. Nitrous acid, HNO2, is a weak acid. Now, this is one of the major constituents in acid rain, because one of the major air pollutants we have are the oxides of nitrogen. The oxides of nitrogen react with moisture in the air to produce nitrous acid, which is then one of the major components of acid rain. We'll talk a little bit more about acid rain, its production and some of its effects at the end of the chapter. But it is one of the major constituents of it. Phosphoric acid, down here, H3PO4. Phosphoric acid, let me come back to that one. Let me just drop down one more here quickly. Sulfurous acid, first of all, H2SO3. Again, we had H2SO4, which was sulfuric acid, which was a strong acid. H2SO3, sulfurous acid, is a weak acid. Okay? Notice that one oxygen less than the strong acid made it a weak acid. Same thing up here for nitric and nitrous. So there must be something about that chemistry. One less oxygen in a strong acid gives us a much weaker acid. Now, sulfurous acid is the other major contributor to acid rain. Anytime we burn coal, coal contains a small amount of sulfur. Sulfur reacts and we emit sulfur dioxide to the atmosphere. Much of our petroleum has a small amount of sulfur in, so anytime we're burning up gasoline in the automobile, we're probably giving off some sulfur dioxide. And it is this sulfur dioxide reacting again with moisture in the air that produces sulfurous acid, which gives us then the acid rain that we're talking about. Now we might get a small amount of sulfuric acid in the atmosphere also, but that is less likely than the sulfurous acid. Now let me go back here then to phosphoric acid just a moment. Phosphoric acid is what we refer to as a poly. Of course, we've used that prefix before. Poly means many, usually anything over 2 essentially. Polyprot, remember, giving off a hydrogen ion is called a proton, polyprotic acid. That means, and there are other ones, a polyprotic acid is an acid that has more than one ionizable hydrogen ion when we put it into water. That's a polyprotic acid. Well, looking at phosphoric acid here quickly then, we can demonstrate this or show this in chemical reaction. The first step in the acid is for the phosphoric acid to give up its first proton to water. We get a hydronium ion and we get what's called dihydrogen phosphate ion. But this ion still has 2 more hydrogens in it, and those hydrogens are ionizable. And so if we continue on, the hydrogen, the dihydrogen phosphate, donates a proton to water. We get another hydronium, and we produce monohydrogen phosphate. Notice the prefix there, mono, meaning 1 hydrogen. And finally, the monohydrogen phosphate donates the last proton to water to give us 1 more hydronium and a phosphate ion in the final form, PO4 with a 3- charge. Now, phosphoric acid itself is the number 7, the 7th most, well, I don't know if we would say important, but certainly from productivity, the 7th most important industrial chemical. I think we've mentioned the one that was the number 1 previously, which is sulfuric acid. Sulfuric acid is the number 1 industrial chemical. And as a matter of fact, as I think I mentioned, that we can pretty much tell about the manufacturing output of a country by monitoring its sulfuric acid production and utilization. Phosphoric acid is the number 7th ranked industrial chemical. Now, the phosphoric acid is produced, and the chemical reaction is quite lengthy, and so I'm not going to write it up here. It is in your text, but it is produced from an ore called fluoroapatite, which is a combination of calcium, fluorine, and phosphate ion. This here then is reacted with sulfuric acid, H2SO4, and in a series of reactions, then this phosphate is converted from here to H3PO4. We also produce some hydrofluoric acid in the process, and we produce a compound of calcium sulfate in the process, which is known as gypsum. But the ore that we start with is called fluoroapatite. As a matter of fact, it's kind of interesting, this particular chemical structure, because it's somewhat similar to what we have making up the porcelain in our teeth. The difference in our teeth is that it is calcium hydroxy phosphate, which is known just as or sometimes called hydroxyapatite. And the problem is, with the enamel in our teeth, is the presence of this hydroxide, because the hydroxide is a base. When we eat foods, and foods undergo then decay, especially sugars in our mouth, are slowly converted to acids. And those acids, if you have sugar against the tooth enamel for a long time, the sugar becomes acidified, and of course an acid reacts with a base, and so what it does is it begins dissolving this calcium hydroxyphosphate. So it dissolves away the enamel in an acid-base reaction. And of course, if you dissolve enough enamel away, you expose the under part, the living part of the tooth, and of course then infection and decay can occur, and you need a filling. And the purpose of fluoride treating a tooth is exactly to change it from this form back to this form here, which is not sensitive to acids, unless you were to drink concentrated sulfuric acid. And if you did that, the enamel on the teeth is probably the least of your concerns at that point. So, but the fluoride treatment then does convert some of the external part of the crown, of the porcelain material, back to this here, which is pretty chemically inert, so that it doesn't dissolve then, and of course that decreases the amount of possible tooth decay. Now, one of the major uses of phosphoric acid was in the production of detergents. Now, to differentiate, we have soaps, which are natural products. We have detergents, which are synthetic products. Detergents are man-made materials that act like soap. But soap itself, the way soap is, it's a large organic molecule which has at the end of it here an acid group. So this end is then, we have a charged end down here, and we have basically a non-charged end down here. The non-charged end, the hydrocarbon end, likes greases and oils. The charged end likes water. And actually in a soap, this has been taken off, and we really have then left behind this minus species. And often we would have something like a sodium here attached to it, sodium compound. So anyway, when you use this, what it is doing is this end down here grabs a hold of oil and grease. This end grabs a hold of water molecules. It likes water molecules. So when you pull a plug, the grease and oil goes down the drain because it's being pulled along by the soap molecules. Okay? Now, what happens if we have hard water? Hard water, and I think I've mentioned this, contains the ion. We saw the conductivity test for hard water showed that we have a lot of ions in there. And a couple of those ions that cause us problem with soap are calcium ion, because a calcium will attach to two of these soaps and make an insoluble solid material. It becomes a solid. And so instead of being able to grab grease and oil and go down the drain, it actually becomes a solid and either precipitates out or floats to the top. In the case of water, this is less dense and it floats to the top, and you get your bathtub ring. You get your scummy looking material on top of the water if you try to use soap in the presence of calcium ion. And that was the purpose for producing detergents then. Something that behaved similar to a soap. In other words, it had to have an end that liked greases and oils. It had to have an end that liked water molecules. And in the process, also had to have something that didn't react with calcium or magnesium ions and make this insoluble solid. Well, phosphates were found to be pretty satisfactory. In other words, if we replace this end right here, which is natural soap, with a phosphate type structure, PO4 structure in there, we produced then a material that had those characteristics. It didn't react with calcium and magnesium and yet had water-liking end and an oil-liking end. But what we found was, and quite by accident and almost too late, was that detergents containing phosphates, phosphate detergents, were wonderful fertilizers. And when you washed the clothes and pulled the plug and the water went down to the lake and the river, along went the phosphate detergent. And it went out into the lake. And there it sat acting as a fertilizer. The things in the lake that are going to use it are such things as algae. And all of a sudden you'd get big algae blooms. Algae would grow wild in the summer. That itself wasn't a problem other than it gave the water a taste and people didn't like it. But more important was that after the algae blooms and grows like mad, it dies. And when it dies, then it decays. And when it decays, it uses up oxygen out of the water. And so all of a sudden we were depleting the oxygen out of lakes because of the phosphate. As a matter of fact, I saw some pictures back in the early days of using detergents where cities were discharging water into the rivers through pipes. At that point we still didn't have as good as sewer systems as we do today, treatment systems, and big piles of soap suds in the river where the water was pouring in from this detergent. The detergent was pretty stable. It didn't break down until algae or some plant used it up as a food. As a matter of fact, some cities were having so much of a problem that they were taking their drinking water from lakes and rivers that this was being discharged into, and people would open their tap to get a glass of water at home and have a head on it. That was not what they wanted, especially the way it tasted. So we finally realized, and almost too late, that phosphate detergents work well as soap substitutes but can create some major environmental problems. We almost eliminated the fish life out of the Great Lakes before it was recovered. It took about 15 years after phosphate detergents were basically removed or at least decreased in the amount that was allowed before the Great Lakes came back. The fish that are most sensitive to oxygen levels are your game fish, trout, bass, pike. Those are the fish that die first because they need high oxygen levels in the water. Things like catfish, things like that, mud bottom, suckers, carp, that type of fish, they can use much less oxygen and still survive. So what we did is we eliminated the good game fish from those lakes. But they have recovered, fortunately, and fortunately we found the problem soon enough that we didn't destroy the lakes totally. This doesn't show up, well, not too badly, but this is kind of what you would see in the summer when you get an algae bloom. This is a pond that's fairly clear water, and then you get this green scum across the top, which is the algae. And as I say, the phosphates acted as fertilizers for the algae growth. That itself wasn't the problem. It was when the algae died and began decaying that created the environmental problem. All right. Well, back to here then. We've now looked at several of these. If we look at the rest of these, actually even the acetic acid that I started with, I probably should have skipped. But look at this one here, has this ending, COOH. COOH, COOH. This one here is written as CO2H, which would mean the same thing. That's just another way of writing it. This one has the COOH, COOH. Down here, COOH. All of these have that particular structure. And those are what we call the organic acids, or we call them then as carboxylic acids. Carboxylic acids. So this is a new organic group we're going to look at. Remember, we've now talked about, of course, hydrocarbons, but we've talked about alcohol, which has that as its general structure, where R is a hydrocarbon and the OH making up the alcohol. We talked about the ethers, R-O-R, that's an ether. And now we're going to take a look at this new group that we call the carboxylic acid group. And these, as I say, are called the organic acids. But look at the structure here. We again have the hydrocarbon group, and then all of them have this same type of structure. A carbon, which has two attachments, two bonds to an oxygen, and has a bond to like an alcohol group. That looks the same as the alcohol group. And this, of course, would be written out as the structural formula, but typically in chemical formulas, we write it as either this, CO2H, or RCOOH. That's the way it's shown in the chemical formula. The simplest of the carboxylic acids is the one made from methane, one carbon. And notice the naming. It's methane, one carbon, and now we drop the E and we add OIC, and then acid, methanoic acid. So if we had something that had 10 carbons, what's the prefix for 10 as a hydrocarbon? Deca, so decane. If we made it as an acid, it would be called decanoic acid. So that's the naming system that is used. The next one, ethane, two carbons, then is known as ethanoic acid by its official name. Now, organic acids have been around a long time, and most of them have, or at least the ones that we commonly encounter, have common names. This one up here is called formic acid. And this one, the ethanoic, is called acetic acid. Those are the common names. So when we go back and look at the chart, we'll see them there, but they're not going to be called methanoic and ethanoic. This is the official IUPAC name. These are the common names that we most frequently encounter. We'll also find that some of the carboxylic acids have more than one acid group in them. This is an example of the simplest one that we have, two carbons with two acid groups. Notice that both ends of the molecule has an acid group. This has a common name of oxalic acid. It is also referred to as a dicarboxylic acid. And of course, one could see where that would come from. Di meaning two, and then carboxylic acid, the COOH groups, so a dicarboxylic acid. Oxalic acid is found, it's fairly poisonous. It's found in the rhubarb family of plants. As a matter of fact, the leaves of rhubarb contain an appreciable amount of oxalic acid. As a protective device, if you would ever observe some rhubarb growing wild in nature, animals, cows and horses, do not eat rhubarb leaves. They have a natural instinct not to eat it. Of course, one is it's sour, but the other is that apparently that oxalic acid triggers a response not to eat it. Now, we as humans more frequently, if we eat rhubarb at all, eat the stalks. The stalks of the rhubarb contain much less oxalic acid, and we more frequently than not eat it in a cooked form. Rhubarb jams or rhubarb pie or something like that. The cooking destroys the oxalic acid. So cooked rhubarb products are going to be no problem. And if we eat a small amount of the stalk, which is pretty sour tasting, we probably aren't going to eat a lot anyway, and it's a pretty low level. But the oxalic acid is potent enough that it can be used as an insecticide, as a thing, not as a sprayed-on insecticide, more as, again, for controlling crawling type insects. Oxalic acid or boric acid can be used. Well, in our next lecture, we'll come back and just take a quick look again at a few more of these organic carboxylic acids, and then go on and talk some about the chemistry of acid-base solutions.